Welcome back to Codex. Today we're happy to feature a talk from Jim Davis from the University of Richmond. Professor Davis is an expert on difference sets and many other areas of algebraic combinatorics. Today he'll be speaking about the search for difference sets in groups of order 256. Take it away, Jim.
Thank you, John. And I have a typical title slide here, but I want to pause for just a second to agree with you that that's a large list of collaborators. And in fact, that list is co-authors on a paper. I've never had a paper with that many co-authors. And just a couple other things of note. One is that the paper was the result of about 30 years of research. So it was a very long-term project, and I'll give indication of kind of the history of where that came from and why this problem was important and where it's going to go next. All of this was initiated by John Dillon, who you see is one of the co-authors there. John was at the National Security Agency for a long time, very interested in difference sets, bent functions, related objects, and drove a lot of the research in the area of difference sets. Two other faculty are Jonathan Jedwab, who is a collaborator of mine for a long time, and Ken Smith. The other four names are undergraduates. And so some of what happens in this search for different sets in groups of order 256 is there was computer programming that needed to be done, and undergraduates are way better at that than I am. And so I utilized their skill set and kind of fed them some ideas that they could program. And that actually was important. And again, I'll describe that as we go along. But I don't assume that everybody looking at this knows what a difference set is. So let's start with, now I did advance. Now it seems to be frozen on me. Sorry about this. Okay, what do I do to...
You can try clicking the right arrow after clicking.
Yeah, I tried right, up, down. Man, we had that.
Maybe click on the slide.
Hey, okay, thank you. Perfect. So here's the example that everybody starts with. It's very easy to follow. So the group, and a difference set is always a subset of a group. And the group in this case is Z7, integers mod 7. And the subset that I want to use is the subset 1, 2, and 4. And as the name implies, difference set, I'm going to be taking differences. The easy ones are 2 minus 1, 4 minus 2, 4 minus 1. We're working mod 7, so you do 1 minus 2, that's a negative 1, but mod 7, that's 6. And the key thing about this is every non-zero element of Z7 appears exactly one time as a difference of elements in my set. That makes that a difference set. Okay? Why would you care? Okay, what does a difference set do for you? Well, one thing is, here's a consequence of that every difference appears once. If I look at the set of translates of 1, 2, and 4, and by that I just mean add 1 and you get 2, 3, 5, add 2, you get 3, 4, 6, and just keep going, working mod 7, I claim that any two of those translates will have precisely one element in the intersection. Okay, and you can just look at it and pick whichever two you want, and guaranteed, if I didn't make a typo, that those will have that property. That turns out to be connected to the Fano plane, the projective plane of order 2, and the numbering isn't quite matching up with the translates that I had before, but I could renumber it. I just found that picture and it was convenient to put up there. The Fano plane has 3 points on every line. Those are the translates of the different set, and any two translates intersect in a point. In projective world, any two lines intersect in a point. And so different sets very quickly get you into some geometry that people are interested in. But a question could be, where did the set 1, 2, 4 come from? And I have a bunch of answers to that. So, actually, before that, let me tell a very brief story that you may or may not know, but I find this interesting. Eric Lander wrote a book in the 80s called Symmetric Designs and Algebraic Approach that guided a lot of research in different sets for many years. It was essentially a book on different sets. But Eric Lander didn't stick around math for very long. He went to teach economics at the Harvard Business School, even though he had never taken an economic, or he had no degrees in economics. He probably had taken some courses in economics. And while he was there, he had a friend who was working on genome stuff. And the friend said, "No way are we going to map the human genome in my lifetime." And Eric said, "I think we will, and I'm going to do it." So he switched over to biology, and he's the lead author on the paper for the human genome being solved. Okay, so quite a pathway that's unusual. He was then science advisor to President Obama, and there's you can read more about him on the internet. But he started his academic career doing different sets, the stuff that we're talking about. Anyway, back to our main thread. Where does the set 1, 2, and 4 come from? One of the places is I claim we could do multiples of 2, or excuse me, powers of 2. 2 to the 0 is, of course, 1. 2 to the 1 is 2. 2 squared is 4. 2 cubed is 8, but mod 7, that's 1. And now you're just going to cycle back through. It's not an accident that the powers of 2 are a different set. Okay, and here's your first Ohio State connection. Marshall Hall was at Ohio State when he was observing things like this, looking in finite fields and cyclotomic classes of this, that, and the other thing, and observing that they often had really nice properties, and he could actually prove some things about that. But that's not the only way that you can see 1, 2, and 4. It's also the quadratic residues mod 7. 1 squared is 1, 2 squared is 4, 3 squared is 9, mod 7 is 2. And if you go through 4 squared, 5 squared, and 6 squared, you're just going to get 1, 2, and 4 again. This was an observation made by Paley in the 1930s. Paley actually was, I think, primarily a physicist, but just I have no idea why he was working on finite field stuff and quadratic residues in finite fields. And nobody could ever ask him about it because he tragically died in a skiing accident at age like 31 or something in Banff in Canada. And I've been to his gravesite. But that's a Paley view of this. You could trace 0 elements in the field with 8 elements in it. And I wrote the primitive element as beta. And you do beta, beta squared, and beta to the fourth, and 0 are the trace 0 elements, but you don't do the 0 element. You're only working in the multiplicative group, so it's beta, beta squared, and beta to the fourth. There's your 1, 2, and 4 showing up. It also, oh, wait, I went backwards. There we go. I don't know why I went backwards. It's connected to the perfect Hamming code. So for those that are on here that like coding theory stuff, different sets often give you error correcting codes with really nice properties. And the additional benefit is you have this group automorphism of the code that can help you with encoding and decoding sorts of things. And one last thing, and I won't go into this for time reasons, but there's a hat game where you play as a team and you either win or lose as a team, and every player is going to guess the color of their hat, but they can't see their own, but they can see their teammates. And you would think that you can't improve on 50-50, but if you have 7 players, you can use this difference set to have a strategy that'll do a 7 out of 8 probability of winning. I'm not going to say any more about that, but lots and lots of connections to all sorts of things. That type of difference set, 731 and projected planes, is not the one that I'm really interested in for this talk. So I want to start with a relatively small example of the kind of difference set that I am interested in. And it is the 1662 difference set in the group Z4 by Z4. Okay, so Z4 by Z4 is an group that, by the way, the parameters at the top, 16 is the size of the group. So I'm working in Z4 by Z4. 6 is the size of the subset. And I've indicated them on that 4x4 grid with little X's. And I've also written the set at the bottom where I'm doing the Z4 by Z4 multiplicatively with X's and Y's, both of order 4, and they commute with each other. I claim that when you do the differencing property or the differencing checking, there are going to be 6 times 5, which is 30 differences from a set of size 6, because you don't do the element with itself, but 6 times 5, the order does matter. There's 30. There are 15 non-identity elements of Z4 by Z4, and I claim that that set will cover those 15 elements twice. And so in the projective plane of order 2, we had 1 solution to any of the difference equations. Here we're going to have 2. This is called a biplane, but it is in a group whose order is a power of 2. And that's where I really want to focus our attention. And the question is, where did that come from? I mean, we could certainly, it's small enough, we could do a computer search, just brute force on that. But we're going to get to things that are way, way too big to be doing brute force searches on. But let me tell you a little bit of the story of the 1662. And by the way, and I think Dustin was the one that observed this, my background, at least it cycles through some things, but it had a paper, and I'm going to show you the paper here in a second. In the 1960s, Kibler did a brute force search of all of the groups of order 16 and asked the question, which of those have a 1662 difference set? And we saw, at least if you believe my claim, that Z4 by Z4 is a yes. It turns out that the cyclic group, and I'm writing it as C16 here, does not. And that might be a little bit surprising in the sense that, oh, wow, cyclic group, that's kind of where differences should exist, and it's not, but That's just the way life is sometimes. But then I have all of the other abelian groups there of order 16. There are 4 others. All of those do have different sets in them. And I'll just comment here that any different set in C2 by C2 by C2 by C2, the elementary abelian group, is also known as a bent function. So for those of you that know Reed-Muller codes and bent functions and Kurdock preparata codes, all of that kind of stuff, that bent world intersects different sets right there. But that's 5 of the 14 groups of order 16. There's no reason why we can't think about non-abelian groups. Okay, and in fact, when you go there, you're not actually subtracting anything, the name different set. It more appropriately would be called a quotient set, where you do A, B inverse, where A and B are elements of the set that you've identified, but the name different set had already stuck, and so that's what people still use. But we can do all the same things with non-abelian groups that we did in abelian groups, and I've written a couple of them down using gap notation for those of you that know gap. Which of those have different sets? And it turns out the dihedral group does not, and I'm using the notation D sub 16 for that. All of the other non-abelian groups do have a different set. Okay, so 12 of 14 groups, you can find a subset with 6 elements in them so that when you do all the quotients, or however you want to say it, differences, quotients, you get every non-identity element exactly twice. That gives us a symmetric design. It gives us an error correcting code of length 16 that you can use the properties of the designs to determine what the minimum distances are. All sorts of things come from that. I'm primarily interested in when do these things exist, so I'm going to carry on with that, but just be aware. Here is that Kibler paper, by the way, and that's what the background was. Somewhere in the mid-60s, I don't remember the exact date. I was going to look it up, but it's got, you can see the 1662 case. There are 14 groups, blah, blah, blah. Cyclic and dihedral don't. All the other 12 do, and some comments after that about what each of those looks like. All right. Well, okay, that kind of in mid-60s, we knew not everything there is to know, but an awful lot of what there is to know about the 16 case. What's the next size? 64, 28, 12. So groups of order 64, subsets of size 28, and every non-identity element has to occur exactly 12 times as differences from the elements. And turns out there are 267 non-isomorphic groups of order 64. And John Dillon, one of my co-authors, said, hey, let's figure out for all of them whether they have different sets or not. Just like in the abelian case, in the size 16 case, when we're looking at abelian groups, cyclic does not have a different set with those properties, nor does C30 C2. Okay, a fundamental result by Turin in the 60s using character theory. Okay, characters of abelian groups being homomorphisms to the complexes under multiplication, and some number theory rule out those 2 cases. The others do, with 2 exceptions, and this is coming from Eric Lander's book, and I'll show you a page from that. C16 by C4 and C8 by C8 were unknown. And that, in fact, those 2 problems were what motivated my PhD thesis, was finding those and then seeing a general pattern for how you could get constructions in abelian groups. And it turns out the answer is yes. This is a page out of a table from Lander's book, and Jed Webb and I independently, so there are actually two papers that came at the same time. This is for all you young people, pre-internet days. So there was no way for me to know what he was working on, and he didn't know what I was working on. We independently came up with things and published. The answer was yes for those two. That finished off the abelian case, but of course, like we saw in the groups of order 16, so we have yeses there, two that don't. Whoops, that went backwards. Come on. There. We also have non-abelian groups. Okay, dihedral of order 64, dihedral 32, direct product C2, some semi-direct products, and so people were banging away on the non-abelian groups. The semi-direct product that I have there is my Colorado State connection. So that is the semi-direct product where you have a generator X of order 32 and Y of order 2, and Yx, Y inverse equals X to the 17. It's called the modular group. And Bob Liebler of Colorado State was circulating a preprint where he argued that that did not have a different set, a 64, 28, 12 different set. And people were reading that, and more or less, people in the area were convinced it was true. Bob's a pretty smart guy, and it seemed likely that it was not going to exist. Ken Smith, on the other hand, did not believe it, and he was working through in great detail, and eventually he had a construction, and he called Bob up, and Bob was insisting that his paper was correct. And Ken, who was a graduate student, he was now, a professor somewhere else, but he was Bob's student, kept insisting that he had a construction. And finally, Ken said, Bob, write these elements down and come back and tell me if it's not a different set. So he read the list over the phone. Bob went and checked and sheepishly came back and admitted, oh, I guess I was wrong. And the construction, that led to all sorts of new things in groups of order 64. With that result, there were 8. I told you there's not in cyclic, there's not in C32 by C2, there's not in dihedral. There's 8 groups that don't have a different set. The other 259 do. So it seems like, and again, this is just an evolving story. Wow, most groups seem to have different sets. What happens the next size up? And that's where we get to, oh, and yeah, the observation, cyclic and dihedral images of order 32, that's the dividing line. And that was true in groups of order 16 as well, where there's a very clean, non-existent result. And if you have a cyclic or dihedral image of order 32, you can't have a different set. Otherwise, you seem to have one. Here's the next size up. 256, and hence the title of my talk, The Search for Different Sets in Groups of Order 256. The size of the subset is 120. The lambda, the number of times you have to get differences, is 56. And I mean, this is way, way out of bounds of brute force kinds of searches that you would have to do. We're going to have to be much more intelligent, but we've actually learned some stuff along the way. The structures that we saw in groups of order 64 carry up to groups of order 256, not perfectly, and there's a lot of weird things that can happen in group theory, but it definitely gives us some insight into how to do this. But the problem is there are 56,092 non-isomorphic groups of order 256. Okay, well, let's start chugging away. And here's a few things that we learned along the way. If you have a normal subgroup of square root order. So in this case, square root of 256 is 16. That is elementary abelian. Guaranteed you have a different set. Okay, that was a result from sort of the mid-90s, was finished off that case. And a lot of groups, in fact, roughly 3/4 of groups of order 256 do have a normal elementary abelian subgroup of square root order. Okay, so that gets 39,000, still leaves us 17,000. Another result is bigger exponent. So if you have a C8 by C8 normal subgroup, the answer is yes. And there was a construction that would work for things like that. We had similarly the non-existent results. If there is a cyclic image of bigger than 32 or a dihedral image of order bigger than 32, the answer is no. Those two non-existence criteria together get rid of 43 groups. Okay, but that still leaves, I mean, we're still at thousands of groups that we don't know the answer to, and people are chugging away on that. What do we do? How do we, and again, the point is not this particular case. The point of this is what kinds of insights do we get into the way that different sets are built, and can we possibly say definitively, ultimately, those two non-existence criteria are necessary and sufficient. That's kind of where we're heading with this, but we're using these test cases along the way. I don't want to spend a lot of time on this because but these are some of the techniques that we used to do some of the searches. Let's say you have two groups of order 256 that have a large subgroup in common. Okay, and maybe it's a group of order 64 or something like that. And we know that one of those has a different set. Well, look at how that different set is spread across the cosets of that subgroup, and then see if you can transfer it over to the group. As groups, they have similar structure. Maybe you get lucky and you get a different set in the group that shares a subgroup. And that worked in a lot of cases. Okay, so that's one sense. Oh, backwards again. I don't know quite what I'm doing there. A second transfer that also handled a good number of cases is get a different set and develop it, take all its translates and look at that design. Calculate the full automorphism group of that design, and then look for regular, in other words, sharply transitive subgroups of the design. And if you have a different one, a different sharply transitive subgroup than the one that you knew, you get a different set in that subgroup. And the most bizarre of all, but it did work, just take the list of elements from GAP. And GAP is a total mystery to me how it works. And so you'll get a list of 120, element number 2, number 7, number 8, 13, whatever. And you just take those elements and stick them into another group and see if it works. And sometimes it does, for reasons that I have no idea what they are, but it did get us some of the more difficult groups. Anyway, a lot of stuff was going on, but ultimately we had 714 groups still remaining. So we were below 1,000. By the way, I don't know if there are any baseball fans in the audience, but 714 is a famous baseball number of home runs Babe Ruth hit in his career. So it was kind of the Babe Ruth number at the time. How are we going to get that down? And here's where I had an undergraduate that was pretty clever. Taylor Applebaum was the first name on the list at the start. And she learned how to program in GAP. And I said, I have a way of constructing things if we have a normal C4 by C4 by C2. And nobody's tried this yet, so let's have you try this out. And there's 693 of the 714. So a big chunk of the groups that remained actually satisfied that list. And I said, just see what you can come up with. And so she went away, and, I just thought, oh man, if we get a couple of hits on this, that'd be terrific. Well, it turned out every single one of those 693 does have a different set. So now, with that result, the hunt was on, because now we're down to 21 groups. Of course, they're the most difficult, and the structures, but some of them behaved kind of like the modular group did that I mentioned with Bob Liebler and Ken Smith from before. But it did take almost 10 years. We weren't working full time on this. We had other things going on, but it took about 10 more years to finish off all of those. And the upshot is they all had different sets. So here's the table that I would show of, groups of order, powers of 2. And notice it's only powers of 4, really, because it turns out different sets have to be in powers of 4. So 16, 64, 256. We now know the complete story for those 3. And in all 3 of those cases, it's that cyclic or dihedral image that excludes some groups from having different sets. Everything else does have a different set. And so what's the next size up? Well, it's 1,024 is 4 to the 5th, 2 to the 10th, and there are almost 50 billion groups of order 1,024. I don't even know how many are excluded. That wouldn't be terrible, but it's going to take something to figure out how many of the 49 billion are excluded. But oh my word, it took so long to get to 56,000. How are we going to get to 50 billion? That seems crazy. Well, I gave this talk in St. Andrews, and Culva Roney-Dougal, some of you may know that name, is at St. Andrews. She's a group theorist, and I was hoping she was going to be there, and she was. And she knows a lot, and in particular, she knows about the classification. How did they come up with 49 billion non-isomorphic groups? A specific number. 487,367,289. That's how many non-isomorphic groups there are, but they are classified. Group 1 has rank 1 and P class 10. That's the cyclic group. There's one of those. And I think group 2 is dihedral group. Okay, so we know those 2 don't have it. And then there are descriptions for each of those. And one of the things that she has started on, and I've started working through, I'm not nearly the group theorist that she is, so I have to look up what all these things mean. But it isn't as daunting because of all the things that we've learned along the way. And I don't think it's impossible to imagine that we'll know the answer to this one maybe in my lifetime. I don't know. It's a lot of groups, but it's broken down into classes. And I think within each of those classes, the answers are either going to be thumbs up or thumbs down. And here's the conjecture that I was willing to make in our paper that I wrote with those 7 other people. And John Dillon doesn't believe this, because he says, well, we've got 3 cases. That's not very much. But the 2 known non-existence criteria, either a cyclic or a dihedral image, are necessary and sufficient for determining the existence of a different set in a 2 group. That would be really great. And I think, groups of order 1024, I mean, again, that's still, if you know that, that's still not the whole thing, but you've got 49 billion things to play with. And it would be very interesting either way for this conjecture. And, I wanted to put it in the paper, and it did show up in the paper, because I think conjectures like this can help focus people's attention on what I think they should be focused on. Is there any way to say why it is that those two things are the boundary, at least in the three that we know, and maybe even in the fourth, and maybe for the whole family? I think that is the place where I want people to be thinking about this. So it's in the paper. So, and this is just a old guy observation. At the start of my career, things that I showed you early on, the Lander table, groups of order 64, we didn't even know whether there was a different set in 16 by 4 or 8 by 8, those abelian groups. We now know the answer for all abelian groups, okay? But there are so many more non-abelian groups. If you go to 1024, I don't remember how many abelian groups there are of order 1024, whatever the partitioning is of 10, is it, but it's 100 maybe out of 49 billion. And the other thing that I comment on here is Ken Smith, one of my co-authors, did a search of the groups of order 64, and even more broadly than that, no, I guess it was just the groups of order 64. He said, okay, let's take every different set in every one of these groups and develop it, and let's look at those designs. And then we'll put those designs into equivalence classes. And when you look at that collection and you separate out the designs that only come from abelian, or it's even stronger than that, the designs that come from abelian different sets, it is less than 0.1% of those designs came from abelian different sets. So in other words, the vast majority of what's going on, both on the group theory side of things, but also on kind of the geometry or the design theory side of things, is in the non-abelian world. And at the start of my career, again, we knew almost nothing about non-abelian groups. And now, okay, we've been able to finish off groups of order 256. We have a shot at groups of order 1024. I think there's still a lot more to be learned in this area. And I haven't even talked about the coding theory connections to that, which are also of interest. So,
Jim,
yeah.
When you say 0.1% of the designs are coming from abelian groups, so you're getting tons of non-equivalent designs from different sets in non-abelian groups?
Tons.
Okay.
And I that's not a very technical term, tons.
Sure.
But it is lots and lots. And I think it was something on the order of 300,000 inequivalent designs coming from different sets in groups of order 64. Don't quote me on that, but it's a large number. And 0.1-ish%, somewhere around there, is coming from abelian.
And the ones in abelian groups are probably like each abelian group has one, or maybe they're all the same or something, right? Like there's very few coming from abelian groups, and they're like all McFarland type or something, right?
So that's a good reference, because McFarland for sure is where you start with that. If you go to the elementary abelian group, which is kind of where McFarland-y kinds of stuff starts, you have 4 inequivalent
Okay.
things, because there are 4 inequivalent bent functions there. And then when you
Okay,
get to
okay.
higher, that kind of explodes. So the same group can have more than one inequivalent design coming from it. So
Thank-
yeah. No, and that actually is my talk. So I don't know if there are other questions, but
I should have waited 10 seconds
I
to
know you
for the
were
Q&A
right there.
session, but now I'll be on the recording, so
Yeah.
or maybe Dustin will edit me out. All right, let's thank Jim for a great talk. I'm going to do that by clicking this button at the bottom of my screen. There we go. Yeah. And